Sure, here's the text punctuated. IA comment from teacher Carlos Candid of Durham College. I've spent my whole life constructing a specific perspective on the world, and now that thought is being addressed, I invite it since it is how we advance in science. James Webb is upsetting nearly everything in cosmology that has been acknowledged as evident for as long as century. Another ultra-profound picture affirms that we have made botches in space science. The telescope that should uncover to us the first stars of the universe is obliterating the earlier perspective and may introduce a new science. Not all scientists are frightened by the new data. Numerous researchers welcome the progressions, since it has long been obvious that something was amiss with our past speculation. The irregularities in estimating the universe's expanding speed ought to have awakened scholars a long time back. Rather than appropriately perusing the signs, they stuck to obsolete ideas. The cosmic microwave background radiation, CMBR, is thought to be the most seasoned in the universe. The CMBR was formed around 380,000 years after the Big Bang, when the universe had cooled sufficiently for electrons and protons to form stable hydrogen molecules. Researchers allude to this change as reionization, and it made the universe porous to light. The CMBR was discovered in 1964 by American physicists Arno Penzias and Robert Wilson while they were fostering another kind of receiving wire. They saw a consistent noise coming from all directions overhead. This revelation was for some time viewed as one of the most compelling bits of evidence supporting the theory of how things came to be. Penzias and Wilson shared the Nobel Prize and made history in astronomy. The CMB most possibly gives a brief look at the youthful universe. Small temperature changes give huge information about the conditions in the universe not long after the Big Bang. Researchers utilized the CMB to gauge the universe's development rate, among other things. Edwin Hubble, a cosmologist, had previously made this calculation in the last part of the 1920s. Hubble found that far-off galaxies recede from us in every direction with speed corresponding to distance. Today, we allude to these estimations as the Hubble rule or the Hubble constant. Of course, Hubble didn't yet have the advanced measurement methods that were utilized many years later when the CMB was discovered. Scientists recalculated the rate, and the new figure is significantly lower than Hubble's original estimate. Later scientists recalculated the rate using type 1a cosmic explosion as the standard candles. Astronomers approach such steady light that it very well may be used as a trustworthy measuring point. The error in determining the universe's expansion rate has existed since the 1990s. From that point forward, scientists have known, or rather thought, that something was the matter with the evaluation of the CMBR, the measuring techniques, or the idea of infinite expansion. The S8 strain or Hubble pressure alludes to the difference between the different measured measurements of the universe's development rate. This has broad repercussions. Beyond a simple estimation difference, the numerous revelations reveal significant insights into how we have previously perceived the universe. For quite a long time, scientists were confused since its beginning. The James Webb Space Telescope has given scientists some unexpected results which may now illuminate the problem of the universe's expansion rate. Worlds so old and mature that their origin probably happened before the Big Bang are completely in conventional science and astronomy. There could be no longer any debate about measurement irregularities. Rather, academics are discussing the most difficult issue in contemporary cosmology. Not only could the universe's expansion speed be wrong, but the whole concept of expansion or the Big Bang is being tested. Webb's photographs reveal evidence of a world that is tremendously different from what we have long accepted. The strain served as a first advance notice, and all scientists who keep on having faith in obsolete theories now face a test. Do we actually know nothing about the universe? Many scientists are now standing on the rubble of their labor of love, gazing into space hopelessly and unable to comprehend how things are playing out. Given the ongoing scientific difficulty, we should ask ourselves, what do we truly know about the universe? To answer this question, we must first grasp how science works. Theoretical scientists utilize a complicated framework of mathematical models, observational data, and logical reasoning to reach conclusions ranging from general to specific. Their expertise relies on a combination of observed events, test data, and extensive theoretical analysis. The name theory alone shows that these are creations and ideas, not reality. We only have practical knowledge as images from telescopes, sound waves, and radiation captured by radio telescopes, and the latest data from neutrino measuring systems or gravitational wave detectors. With the James Webb Space Telescope, we now have equipment at our disposal that allows us to analyze the earliest light into individual frequencies and examine it in ways that were previously impossible. Webb can show us which elements were prevalent in galaxies long ago, how much mass was contained, and how many stars. This proves the telescope can reconstruct a system's structure and direction of travel. However, Webb might have flaws in some of its photographs due to massive gradation circles. The telescope can't tell us whether we are looking at galaxies or black holes that shine as brightly as galaxies. We must confront the fact that our science has long accepted too many potential outcomes as facts while ignoring alternative explanations. Research has long been confident that it is correct. The most recent findings from the James Webb Telescope provide crucial clues to replacing ideas with new insights, as has happened many times in science. Researchers are already waiting. The new results are too strange, and it seems impossible for some scientists to come up with new interpretations. At the moment, the new discoveries are challenging the basis of current physics, which alarms many scientists. Current physics courses are mostly based on Isaac Newton's discoveries in the 17th century. For centuries, his principles of motion and gravity served as the foundation for our physical understanding of the world, including the universe. Newton's rules figured out the movements of objects under normal circumstances and worked well on Earth. In space, however, his ideas needed to have been expanded, which Albert Einstein greatly refined at the turn of the 20th century. His special theory of relativity, published in 1905, changed our view of existence. Einstein showed that space and time are linked with each other and depend on the movement of the observer. The general theory of relativity, published in 1915, expanded the concept by providing mathematical evidence of gravitational anomalies based on the arc of spacetime caused by masses like stars or galaxies. Einstein's theories and ideas were mostly firm, yet he approached his limits throughout his life. The researcher knew that his theories could never be sufficient to describe the entire universe. He wanted to find the world formula, but he did not succeed. Strangely, no other scientist has succeeded up to the present day. Where's the mistake? Wouldn't it be interesting to know where the mistake is? Makaku, a prominent astronomer from the US, stated in a meeting that the person who answers this challenge will surely win the Nobel Prize. Let us research what facts scientists might have overlooked, where they may have confused events, and whether our telescopes are to blame. Dark matter and dark energy are among the most likely sources of the cosmic catastrophe. Our recent theories of the universe combine the idea that dark matter and dark energy together account for around 95% of the universe. However, neither has ever been directly observed, and thus their actual existence has never been outlined. It is possible that they do not exist at all, and we must determine the universe's expansion and galaxy elements separately, or both have properties that we do not yet understand. One theory now being explored is that the physical properties of the two dark components have evolved over time, which could imply that we are dealing with some form of intelligence. The next thing to be tested is gravity. This force, which seemingly causes attraction or curvature in spacetime due to mass, has yet to be demonstrated. Einstein is primarily responsible for the concept of spacetime curvature, which has been repeatedly proven correct. However, we cannot rule out the possibility that gravity has completely different characteristics than previously thought, or that the gravitational force between objects is caused by a different mechanism. Several values known as fundamental constants have been outlined in modern cosmology and astronomy over the years. These values are generally reliable because they rarely change. Measurements have revealed that slight fluctuations in these specified constants introduce new energy into the universe, allowing us to figure out different events. Without the existence of dark energy, it is also possible that our interpretations of the redshift of light are incorrect and that we have been measuring incorrect distances within the universe and determining the ages of galaxies for centuries. Perhaps our beliefs about the universe's original state were also wrong. We might have misread the cosmic microwave background radiation. It's also possible that the universe can't be traced back to a single starting point. This would suggest that the Big Bang Theory,